All right, so for the notes on page 23 and 24 of your packet, we're going to be doing some problems that include energy bar charts. But unlike yesterday's homework, we are going to be talking about more than one type of energy at the same time. And so then what we'll be able to do is calculate the total amount of energy an object has at one point, and then calculate either the velocity or the height of the object at a different point in time, based on the fact that their total energy is conserved. So for this first problem, it says that a person throws a ball straight up into the air with a velocity of 20 meters per second. The mass of the ball is 0.7 kilograms. How high does the ball get? And so then it tells us that initially the ball is moving. So that's what this picture down here, picture A, is. And then picture B is when the ball is at the top of its flight. And so it's not moving anymore, but it is higher up in the air. So if we're looking at these two pictures and we're trying to make an energy bar chart, the first thing that we'll do is write down the name of the system in the circle, which is the ball. And then we'll look at what kind of energy does the ball have at the beginning. Since the ball is moving at the beginning, we can say that it has kinetic energy. And since the ball is not moving but higher up in the air, we can say that it has gravitational energy at the end. And notice that the total amount of EK that the ball starts with is equal to the total amount of EG that the ball ends with. And so the total energy that the ball has is conserved. It's the same. Then what we can do is we can start to, well, let's write the energy equation first before we go up and identify some variables. So the energy equation for this energy bar chart would be that the kinetic energy is equal to the gravitational energy. And again, that just shows that this bar is equal to the size of that bar. Now what we can do is go back up to this section and fill out what variables we see in the problem. And so I'm going to circle some of the clues that tell us about the situation, and then we'll be able to identify what each number or words tells us. And so the 20 meters per second, it says right before that this is a velocity. And so I'm going to write that on the line next to V for the velocity of the ball. The next number that they give us, 0.7, is labeled as the mass. And so mass is represented with the symbol M. And then G is actually up here in our equations. It's always the same number. It's called a constant, which is 9.8. And the last thing that it asks us for is how high does the ball get? And so when we're talking about how high something is, we need to know the height. And since we don't know, it's not given to us in the problem, I'm going to put a question mark there because that's the value that we'll be solving for. This is useful because eventually what we're going to be doing is plugging these values into an equation, and we want to make sure that we're putting the right number value in the right spot in our equation so that when we calculate it and do some algebra, that we're getting the correct final answer. So now in part B, it says to replace the energies with their formulas. So I'm going to go to the top and look for an EK formula. The one that I see is this one. And so the EK formula needs to go in for this side, and then the EG formula needs to go for the other side. And so what that looks like is 0.5 times mass times velocity squared. That is the EK equation. And then M times G times H is the EG equation. And so because our energy bar chart tells us that these two amounts of energy are equal to one another, then we know that the formula that you would use to calculate either of them is also equal to the other formula you would use to calculate the other one. So the last step says to substitute numbers that you know and solve for the unknown number, which in this case is height. So I'm going to plug in all of the numbers that we have. When I get to the variable M, I'm going to plug in the mass of 0.7 kilograms. For velocity, I'm going to plug in 20 meters per second. And then I'm going to do the same thing on the right side. Mass is 0.7, G is 9.8, And h we don't know, so h I'm going to leave as a variable, so that way we can solve for it, kind of like the variable x in math. So on the left side of this equation, I'm going to use my calculator and multiply 0.5 times 0.7 times 20 squared and get 140. Then I'm going to multiply these two numbers to see what the coefficient in front of h is. So 0.7 times 9.8 is 6.86 times the height. And so in order to calculate what the height is, what we need to do is divide both sides by 6.86, because if we do that, then we will cancel it out from the right side and isolate just the variable h. So in my calculator, I'm going to plug in 140 divided by 6.86 and get that the answer is 20.4. Meters are the usual unit for height, and I'm going to round it just to the 10th place for this problem. For the second problem, we have a worker standing on top of the 33.5 meter tall Greendale Water Tower, accidentally drops his 2 kilogram wrench and it falls to the ground. How fast is the wrench moving when it hits the ground? And so you'll see on the drawing right here. So in the picture that I drew on the left, we have a wrench that's high up off the ground at the beginning, and then it's falling at the end. And so at the beginning, because it is high up off the ground, it has gravitational energy. And then when it is lower, it doesn't have any more, but it's moving very quickly at the end, and so it has kinetic. I forgot to write in our system, which is the wrench. And so our energy bar chart can lead to the equation that says that the amount of gravitational energy that the wrench has at the beginning is equal to the kinetic energy that the wrench has at the end. We can look up at the problem and identify some numbers. So the first number is how many meters the water tower is tall. We can write this down for the height, 33.5 meters. It says that the mass of the wrench is 2 kilograms. And then it asks us for what the velocity is afterwards. G, once again, is a constant, which is 9.8. And so now we know 3 of the values, and then we are trying to find the fourth one that is unknown, which in this case is the velocity. And that's what the question is asking for, which is how fast is it going? What's the velocity? So we can then write these two equations in for EG and EK. EG is the bottom left equation, which is mass times G times H. And then EK is the one at the top left, which is 1/2 times mass times velocity squared. Then we can sub in the different values that we wrote down over here into these two equations. And so we get these forms of the formulas with all of the values plugged in. And for the left side, I'll multiply 2 times 9.8 times 33.5 to get a product of 656.6. And then on the right side, I'll multiply 0.5 times 2, which gets us just 1. And 1 times v squared is just v squared. So now I have to take the square root of both sides in order to get just velocity instead of velocity squared. And so if I type in the square root of 656.6, I get that the answer that just the velocity would be 25.6, and then the units for velocity are meters per second. And that would be our final answer for how fast the wrench is going at the bottom.